Today we will be presenting our Chapter 5 Chemistry overview by me, Donovan, and my group mate Fabio. So first we will discuss the valence shell electron pair repulsion theory, otherwise known as the Vesper theory. The Vesper theory can be used to predict the structure of molecules. The Vesper theory states that since electron pairs are negative, they will repel each other and will prefer the geometry that places electron pairs the furthest away from each other. And we can use the Vesper model to predict the geometry of most polyatomic molecules and ions by focusing on their electron pairs around the central atom. In order to use the Vesper theory, we have to know the electron pair geometry. And in order to do this, we must draw the Lewis structure and find the steric number of the molecule. So the steric number can be found by adding the number of atoms bonded to the central atom with the number of lone pairs on the central atom. And the steric number is used to express how many regions of electron density surround a given atom. And because we know that electrons will repel and find the arrangement that places them the greatest distance away from each other, we can now find the molecular geometry and bond angles of the molecule. So in this image here, we can see the different molecular geometries which are dependent on areas of electron density. So if we have a steric number of 2, then that also means that we have 2 electron dense areas. This means that the geometry is linear. If we have 3 electron dense areas, then we have a trigonoplanar molecular structure. However, if we have a lone pair, then the molecular geometry is bent. This is due to the fact that the lone pairs that are attached to the central atom will still repel the other electrons. And if we have 4 electron dense areas, then we have a tetrahedral molecular geometry. We can use the steric number and lone pairs to determine other molecular geometries as well, such as trigonal, bipyramidal, and octahedral. And that basically summarizes how we can use Vesper theory and steric numbers to determine molecular geometry.
Let's go ahead and talk about how to identify polar and nonpolar substances, as well as atomic hybridization and valence bond theory. So starting with polar and nonpolar substances, polar molecules are those where electrons are shared unequally. Polarity is a result of bond nipules, which is when there's a partial separation of charge in a bond, meaning that one end is slightly positive and the other end is slightly negative. And this is due to differences in electronegativity between atoms involved in a bond. Since one is more electronegative, it's going to have a stronger pull on electrons and therefore have the slight negative charge. And to predict whether a substance is polar or nonpolar, we take the sum of the vectors of these bond dipoles, and if the sum is equal to 0, we have a nonpolar molecule. If the sum is not equal to 0, then we have a polar molecule. Another way we can get a nonpolar substance is if the bonds are all nonpolar, which would mean that the electronegativity value of both the atoms involved in the bond is equal to each other, but this rarely happens. And the longer the vectors, the greater the bond polarity, again because that just means that there's a greater difference in the electronegativity value of the atoms being involved in the bond. So let's go ahead and take a look at the first example at the left of the presentation slide. So we have CO2, which has a linear geometry. So as you can see, there's 2 oxygen atoms, one located at the left and one located at the right, at exactly opposite directions. So both have a higher electronegativity value than carbon, so they're both going to pull in the electrons and have the slight negative charge. So since they're in opposite directions, they're going to cancel each other out, and therefore CO2 is a nonpolar molecule. Also keep in mind that it still has temporary dipoles since bonds do fluctuate, but since it doesn't have a permanent dipole, it's still considered nonpolar. So moving on to the second example, which is H2O. Oxygen has a higher electronegativity value than hydrogen, so it's going to be pulling on electrons at a higher degree. So the negative charge is going to be oriented towards the oxygen at the top of the molecule, and since it has a bend geometry, the vector is going to be pointing upwards, and therefore it's a polar substance that has a slight negative charge at the top of the molecule where the oxygen is located and a slight positive at the bottom where the hydrogens are located. So moving on to atomic hybridization and valence bond theory. Valence bond theory is when bonds are describes a concept where bonds are created due to the fact that atomic orbitals are overlapping and different orbital combinations produce different shapes. So whether it's one s orbital and one p orbital overlapping, or one s and two p orbitals and so forth, and all the orbitals overlap because both the nuclei are attracted to the electrons of the atoms they're bonding to, and bond angles are based on the distance between these hybrid orbitals being maximized since electrons repel each other, so they want to be as far as possible, and bond angles will reflect this repulsion. And there's three main forms of hybridization we'll be talking about in this class, but they're not limited to these three, with the three being sp squared, and sp cubed. All three tell us which orbitals are being involved in the overlapping, with sp involving an s and a p orbital, sp squared involving an s and two p orbitals, and sp cubed involving an s and three p orbital. There's also two types of bonds, the first being sigma bonds, which describes when electron density is increased on the same axis as the atoms, and pi bonds, which is where electron density is increased above or below the same axis as the atoms being bonded.
So now we will be discussing chirality. So a molecule or ion is called chiral if it cannot be superimposed on its mirror image by any combination of rotations or translations. So for example, if we put our hands together palm to palm, we can see that our hands are mirrored images of each other. However, if we try to place our hands on top of one another or superimpose them, we see that they do not match. So this means that our hands are chiral. So why is chirality important? Well, let us first discuss isomers. Isomers are compounds that have the same chemical formula but have different molecular structures. Isomers that differ in spatial arrangement of atoms instead of their atomic connectivity are called stereoisomers. And enantiomers, which are a type of stereoisomer, are non-superimposable mirror image molecules of each other. So this means that enantiomers are chiral. The chemical properties of a chiral molecule may differ greatly from their mirror images. So this is important because organisms may recognize and respond to chiral molecules differently. A molecule that has 4 different groups arranged around a central atom is called a chiral molecule, and the central carbon is known as a chiral carbon. Now, a stereocenter is an atom that is bonded to 4 different unique atoms. And if we look at this image here, we can identify that this molecule has 2 stereocenters because that is where carbon atoms are bonded to 4 different atoms. However, it does not have a stereocenter at the bottom because the carbon is bonded to 2 other carbons. And that will just about wrap up chirality.
Moving on to molecular orbitals. Molecular orbitals are like atomic orbitals, except that instead of belonging to a single atom, they belong to the whole molecule. Similarities between both include the wave function, which is still based off the Schrödinger equation, the same quantum numbers apply for both, and the principles to predicting where electrons are the same in both as well. In addition, there are energy levels to MOs, like in atomic orbitals, and this can explain the visible spectra of MOs. Like in atomic orbitals, electrons in the MOs can be excited when electromagnetic radiation is absorbed, and when they transition back to the ground state, radiation is emitted and seen as light, and this makes up the visible spectra of the MOs. And when drawing orbitals or MOs, remember that the MOs are equal to the amount of atomic orbitals combined, and that there's two types of orbitals, antibonding and bonding orbitals. Bonding orbitals are lower in energy than antibonding orbitals, so they're going to fill up first. And then another advantage of molecular orbitals is that we can use them to predict bond order. So by taking the total of the bonding electrons and the antibonding electrons, we can subtract the antibonding electrons from the bonding electrons, divide that by 2, and this gives us the bonding order of the molecule, or the atoms in the molecule. And the MOs can also be used to explain magnetism. So as you already know, electrons spin either up or down, and this is represented by the quantum number m sub s. So when an electron doesn't have a paired electron, this creates a net spin and creates a slight attraction to a magnetic field, also known as paramagnetism. And then when electrons are paired, the up and down spins of each electron cancel out, and this causes there to be a slight repelling nature to magnetic fields. And then moving on to drawing an MO diagram, we're going to go ahead and draw an MO diagram of N2, which is the diatomic molecule for 2 nitrogen atoms. So we're going to start by taking the total of the valence electrons, which is 10, since each nitrogen atom has 5. So first we're going to go ahead and draw the antibonding and bonding orbitals for the 2s orbitals. And we go ahead and fill this up, since, as we stated previously, we have 10 valence electrons. Then we move on to the 2p orbitals, and we see that we have a sigma 2p orbital, a pi 2p orbital, pi star 2p orbital, which represent the antibonding orbitals, and the sigma pi 2p orbital, which also represents an antibonding orbital. So when we go ahead and fill those up with our 2p orbitals, with the 2p electrons, we see that we only managed to fill up the sigma 2p orbitals and the pi 2p orbitals, but don't manage to fill up the antibonding orbitals. So in calculating the bonding order, we see that we have 8 total bonding electrons and 2 total antibonding electrons. So when we subtract that, we get 6, and we go ahead and divide that by 2, and this gives us 3. So we know that the diatomic molecule for N2 has a triple bond, which makes sense since each N has a bonding capacity of 3. Thank you for listening to our presentation, and I hope you have a good day.